Hello, welcome to our continuing series of talks on what's new in version 12 of the Wolfram language. My name is Brett Champion, and we'll be talking this afternoon about geographic visualization. And so geographic visualization is an area that we've been steadily working our way through since we initially added geographic support a few years ago. And it's just sort of an interesting area, and we're continuing to roll out new classes of visualizations for looking at different types of geographic data. And so in version 12, we added four new visualization functions for geographic data: Geo Bubble Chart, Geo Smooth Histogram, Geo Vector Plot, and Geo Stream Plot. And we'll just take a quick look at each of these before we start looking at a few of the examples in a bit more detail. So the first one we're going to look at is Geo Bubble Chart. This is the geo analog of Bubble Chart. And so, and all four of these functions that we're going to be looking at have non-geo versions that they are closely related to and rely on under the hood and whatnot. So Geo Bubble Chart is going to take a location, a geographic location, and a value, and it's going to represent that value by a bubble where, generally speaking, the size of the bubble is going to correspond to the size of the value. So larger values are going to result in larger bubbles, and larger and smaller sizes of the value are going to result in smaller sizes of the bubble. And so here we have an association that has the 50 largest cities in the US and their population in an association. And so just to take a quick look at what this data set looks like, because it's not always the fastest thing to generate, although I think speeding that up is underway again. And so here we have an association with a bunch of cities from Albuquerque to, well, we don't quite get to anything that starts with a Z, but to Wichita. And each of these then has a population, which is a quantity with units people. And so then you can sort of see that New York City is 8.6 million, is the largest of the 50. And the smallest, let's pick, what was that, Kansas City? It's just under 500,000. Looks like Long Beach at least is a little bit smaller, and Miami. So we've got a couple of similarly sized bubbles here in Florida and some in California and whatnot. And so that's the basic idea. There's different ways that you can input the data as an association. You can put the locations and the values in a list as a pair, and provide lists of those. But generally, it's going to be a location and a value. And then you get to use sort of all the features and machinery that the non-Geo Bubble Chart has available to it. And so there's an option that controls how big the bubbles are. So 0.05 to 0.35 means that that's going to be sized roughly on the diagonal of the data. It's looking, or actually, it's probably closer to about the height in this case. So we get about 3 of these New York City bubbles from top to bottom, and probably about 20 of the Kansas City, Miami, Long Beach ones. So you can control how big the bubbles are. You can control what the styling is. So in this case, we're using a plot theme in addition to changing what the bubble sizes are a little bit to control a large number of style changes at the same time. And so it's changing the style of the bubbles. It's changing what the base map is, what the background is, to a relief map of the contiguous US. And we'll see some more examples later on of doing more advanced things with Geo Bubble Chart. So the next one that we're going to look at is GeoSmooth histogram. And so the general rule is you knock the geo off, and then you have your corresponding normal visualization function, or your non-geo viz function. And in this case, it's a little bit different because this is actually the equivalent of smooth density histogram, but we felt that the geo sort of hinted enough at the fact that it's location data that you're looking at. And so this is a data set that's just taking a bunch of locations. In this case, we have a data set of all the breweries as of, I don't know, it was like 2012 or something, in the contiguous US. And the geoposition actually happens to show what the distribution of underlying points is. And so a lot of stuff in the Northeast and sort of the upper Midwest and then along the West Coast. And then what you do for the GeoSmooth histogram is you have typically a Gaussian type of bump that you put over every point, and you add these all up. And the higher that accumulation gets, the darker the representation is. And because you have a Gaussian, then everything over the bump sort of has a tail that's going to fall off as things move farther away from that point. And so you get these gradients that sort of smooth out where everything is. And so you can see a lot of density in the upper Northeast and the upper Midwest, along the West Coast, and a sort of noticeable cluster around Colorado, a little bit in Florida, and a little bit in Texas. And so one of the big controls for smooth histograms, or which is kernel density estimation, which is what other people may know it by. And so is that you can sort of control what the shape of that Gaussian is. So sort of how quickly does it fall down to effectively zero? And that's called the bandwidth, and that's what the second argument of GeoSmooth histogram is here. And when the bandwidth is smaller, each of those bumps is a bit more of a spike. And so you get sharper peaks that fall off more quickly. And when the bandwidth is wider, then it's more of a hill, a nice wide hill, and you get more blending between regions. And you see that our upper Northeast and our upper Midwest sort of all merge together into one general peak, and the West Coast and Colorado sort of flood out to cover the entire Western US almost. And so here we'll look at another instance of using a theme to change what the plot looks like. In this case, we're using the detailed theme, which is going to give us a legend and scale bars, so we have some idea of how big the US is. And the legend for the scale bar is actually going to tell us two things. So one is it's going to tell us what the sort of the measure is, which these numbers aren't necessarily the most easy or natural things to interpret, but it allows you to better map, say what's a factor of 2 or something. But the other thing is that along the left-hand side of this scale bar, we have a thin gray line that goes from sort of white to a darker gray. And that is a representation of how opacity has been factored into this map. And so what happens, especially with GeoSmooth histogram, is if we don't vary the opacity, then the entire map is going to sort of get mapped to this bottommost color, because the tails never stop on those distributions. And so they're going to sort of blanket everything. And so we have an option, actually 2 options, opacity function and opacity function scaling, that control sort of a cutoff or a fade out of the density, the smooth density that we're looking at. And this allows sort of the almost 0 parts of the data to disappear as they fade to being completely transparent. And then that also helps to draw attention to the parts that aren't transparent, where you have some meaningful level of the distribution. And I see in chat that somebody's commenting about the stuff bleeding over into the oceans, and which doesn't necessarily make sense. I mean, you'll notice that it also fades over into Canada and parts of Mexico, which aren't part of our data sets. I mean, I'm sure there are breweries, especially in this part of Canada. And a little bit later, we'll look at some ways of dealing with that. I think we came up with a really nice solution for that and a very easy way of dealing with it. So the next 2 viz functions are the geographic visualization functions, are Geo Vector Plot and Geo Stream Plot. These are the geo versions of List Vector Plot and List Stream Plot. And so each of them is going to take a location and a vector direction, or direction and magnitude, at a set of points, and it's going to interpret those as a continuous field across the Earth. And so for Geo Vector Plot here, we're looking at wind data, wind vector data on January 1st of this year. And in particular, we're looking at the downwind geovector. And a little bit of background on this. And so a couple things. One is that the downwind geovector means that the vector is going to be pointing downwind. A lot of times when you ask, or when what wind direction gets reported, it's reported as the direction the wind is coming from. And so we added in version 12 this additional argument to wind vector data to allow us to control that, because we want the vectors to basically point in the opposite direction from which they're typically reported. And so we did that by allowing the data to be reported that way. And so then we see that there's some, you can sort of see what direction the wind is blowing. It's not the most beautiful plot. It's looking like in version 12.1 this should be improved quite a bit, as we are trying to get the automation behind the vector plots improved quite a bit. And so here we're going to increase the number of vector points, and you get a little bit more filling in of the gaps to see where things are. But there's still sort of the issue that where the wind is not very strong, it disappears a little bit. And of course, when we use more vectors, then they have to get smaller, and it can be a little bit harder to see what the field is going to look like in that case. And so in this case, we're going to scale the vectors. we're going to put them on a log scale, essentially. We're going to scale the magnitudes so that there's not such a big gap from from weak to strong, and things are going to show up better. And then we can change the shape of the vectors to sort of a drop shape marker. And that can also be useful, at times in looking at what the vector field looks like. The other thing that I wanted to mention is, and we'll put this under Geo Vector Stream Plot, is what this data looks like. So the data in this case is actually a GeoVector object, and it's not going to be the most prettily typeset thing because there's actually a lot of missing data here. And so, yeah, I did 250 points. And so the GeoVector has 250 locations, and then it is using rule in this case to associate the angle and magnitude and angle of each of those vectors. And so GeoVector is going to, as I said, give us a magnitude, in this case in miles per hour, and a direction in degrees. There are other ways of specifying vectors. So in particular, there is GeoVector ENU, which roughly stands for east, north, and up, in which case you can give the vector in the Cartesian specification instead of a polar specification. And so we'll jump right into GeoStream Plot, and this is a slightly different data set. This is from about a year ago when we had Hurricane Florence menacing the eastern seaboard of the U.S. And so we got we sampled some of the data at that time and recorded it. And so this is very similar to the Geo Vector Plot. The difference is that the streamlines are a bit more continuous. It's easier to see what the directions are for where the field is going, at the expense of knowing what the strength is. And so this really doesn't show us the magnitude at all. This is really focusing on the direction and what the flow is. And so we can change the style so that they are, say, red and show up a little bit better. Or we can change the theme, in this case to marketing, in which case we get sort of this dark background combined with a brighter set of streamlines on top of it. And so now we'll look at some of the sort of advanced features of the visualization functions a little bit. And like I said, all of these have non-geo analogs, all equivalent functions for regular data. And they share the same options and, generally speaking, the same functionality. Occasionally there may be something that doesn't translate to the geo case for some reason, or that only makes sense in the geo case, in which case you may have something that works in one function but not the other. But we generally try to minimize that sort of discrepancy. And so for the Geo Bubble Chart, we're going to look at some of the labeling functionality that was added recently for bubble charts, in particular callout. And so in this case, we're looking at a data set that is, for every country in Europe, we're getting the entity, so what the country is, and what the GDP per person is. And it's sort of enough information for us to do some interesting things from. And so we're going to create a call out for each of those. So the slot 2 is going to be our entity and our country, or sorry, our entity and our GDP per person employed. And then the label for the callout is just going to be the entity again. And so then we see that Ireland has a relatively large GDP per employee. Same for Germany. Ukraine and Moldova are on the smaller end of that scale. And so what doesn't necessarily come across well on this as a web thing, at least not at the moment. It'd be interesting to see how hard that is to improve. Actually, in cloud, it might be okay. But anyway, so where there's space, we're using the country names to label things. Where there isn't space, so like in Central Europe here, where we get lots of things sort of stuck together, each of these bubbles would actually have a tooltip on it with the country name. But there's sort of not enough space to fit a label for Germany in without it colliding with the other bubbles, and so it doesn't get displayed. And so in the next example, we're going to try to get around that a little bit by changing what we're using for the label. And so instead of the full country name, we're going to use the country code, which is 2 letters, much smaller. And then there's a couple things that happen. So Germany still ends up with a tooltip in that case. We now have a label for Portugal and a few other countries that didn't have labels before. But for the labels that are sort of small enough compared to the bubble size, in this case, the automatic positioning for the callout is able to put the label inside the bubble. And so we have Ireland and the Netherlands and okay, what country is that? That's big. That must be Luxembourg. Sorry, not Germany. Luxembourg or Liechtenstein? My detailed knowledge of European geography is failing me at this point. But Switzerland and so on. And then we can change what the style of the callouts are to sort of a balloon appearance and get a different rendering. And so moving on, let's see. Right, so I talked a little bit about opacity function when we were looking at the legend for the GeoSmooth histogram the first time. Here is another data set with all the trees in Champaign, Illinois, that are sort of the responsibility of the city. They have a big database of all the trees and what type they are and how big they are and whatnot that their arborist uses for knowing where to look for, say, elm trees that are, ash trees that are of late being ravaged by a beetle and being killed off. But so when they know that there are things affecting different types of trees, they know where all of their trees are, so they can go inspect things and perhaps apply treatments or do trimming or whatever. And so in this case, we're going to change the color function to something that's green colored in honor of the trees. We can change how we apply the opacity, which affects sort of how much the base map shows through and how dark things get and whatnot. And then we'll get to region function, which, so there was this comment earlier about the GeoSmooth histogram flooding into the ocean, even though there are clearly no breweries there. And so region function was first introduced into the language in version 6 for a bunch of the scientific visualization things. And normally it is a function. You pass it slot 1 through, slot 2, whatever, and you construct something, and it's, it's okay in that sense. But for Geo, we realized that we could do something much more clever, which is that we can extend it to, say where you give us the entity that you're interested in, or possibly a polygon, and we can take care of effectively computing a function, or creating a function that can be worked with efficiently. And so in this case, we have cities in Italy, by population. And when we say region function goes to Italy, then it automatically trims that smooth histogram to the boundary of Italy. And so it doesn't go into, the Mediterranean, and it doesn't, bleed over into into Switzerland or any of the other neighboring countries. And you get just the density over Italy. And we actually have the same support for Geo Vector Plot and Geo Stream Plot. In this case, we're going to look at Geo Stream Plot, and we're looking at, this looks like weather data again, in miles per hour. And so we can look at what the wind is doing just over Italy, ignoring, places over water or whatever. Which is actually sort of useful a lot of the time for weather data, because a lot of the times you don't have nearly so well a resolution of, or monitoring of, weather over oceans as you do over land. Not as many stations in place. And then when we were looking at Geo Vector Plot, we sort of alluded to this a little bit, that you can change what the marker is for the vectors. And there's, if you look at the documentation for vector markers, there's tables of more than a dozen different shapes that you can use, and they generally work in Streamplot as well. A few of them perhaps aren't quite as interesting in Streamplot, but you can sort of use those to change what the shape of the markers is and how they look, and then they could, you can change the coloring and whatnot just as easily. I think so. I'm going to pop back out to the main page just to double check. Okay. So I'm going to pick and choose from the last 8 examples, sort of the more applied ones, a little bit in terms, well, no, we'll hit them all, just some of them a bit longer than others. So this is sort of our initial example of something using GeoSmooth histogram, which is looking at earthquake data. So we're looking at a 10-year span of earthquakes in Japan of at least magnitude 3. It's wrapped in quiet because earthquake data likes to warn you that it may be including the same earthquake multiple times, or that it's going to treat some of them as duplicates. But basically, almost any call to earthquake data is going to issue a warning about if you're doing it over a longer span. And so here's sort of the raw data, the individual locations that we have. And then we can use a GeoSmooth histogram to look at that data. And again, we're using the region function to clip it to the landmass of Japan. Otherwise, it would, you would see noticeable stuff over here in the ocean off on the east side. The next 2 examples are going to be applications of Geo Bubble Chart. Both of them are examples of changing what the bubble looks like. So in this case, we have all the countries, sorry, not all the countries. We have the 25 largest countries by population. And then for each of them, we're going to create a pie chart of what their fraction of child, adults, and elderly populations are. And then we're going to use chart elements to use those pie charts as the bubbles, and those will then be automatically sized according to the values. And we're going to label them to the extent that we can. And then we add a legend identifying the child, adult, and elderly populations. And it's sort of interesting looking at the resulting map. And so you have, say, the US and a lot of Europe, a little bit less so Europe, where the child and elderly populations are about the same, and the bulk is, your sort of your adults. A lot of the African countries are predominantly child and adult, with much smaller elderly populations. And then if you look at, Japan, you start to see more of the elderly population compared to the children and the adults. And so it's interesting to sort of see how things break down based on parts of the world and whatnot, and how different countries have developed over the years. And so the next one is, I think, a really cool looking plot, which is similar, except instead of using the, creating a pie chart for each bubble, we are using an image of the flag for each country. And they're sized and in this case, they're sized by land area, which has the cool effect that they basically cover all the land mass. I mean, so you get, Alaska shows up here a little bit, part of Russia, Antarctica isn't, is an independent territory and not claimed by anyone for the most part. And then you get a bunch of little islands. But you sort of have a map of the U.S. or not of the world, entirely out of the country's flags. And it came out looking much cooler than I expected it to at first. And so, but as before, this is just an application of using chart elements, and in this case, we're using the Lambert-Azimuthal projection to map the entire world to a disk. And it comes out looking pretty cool, I think. And then here's an example that the web page is broken, which I knew it had forgotten. So we'll skip that one for the time being, and then I'll have to figure out why it's not looking right on the website. And so the last four examples that we have are sort of, I think, sort of the more intense applications of the GeoViz functions for the most part. Saving the best for last, so to speak. So the first is an application of Geo Vector Plot, and I think Geo Stream Plot. Geo Vector Plot for sure. Where we're looking at a particular crater on the moon. And so we're looking within about 75 kilometers of the center of this crater. And we're using geo elevation data to get the elevation around, covering this area. Strictly speaking, it should perhaps be, a separate function of lunar elevation data, but it's perhaps a bit too specialized. So the extraterrestrial stuff we're just including with Geo, generally speaking. And then based on the elevations, we're going to interpolate, create an interpolating function of the elevations, and then we can compute derivatives of the interpolating function to figure out sort of what the slope is, what the gradient field is for this area on the moon. And in this case, we're using GeoVector E and U to look at a horizontal component and a vertical component instead of angle and magnitude and direction. Sorry. And so we get a bunch of vectors, and then we can plot the vector field. And so in this case, the color function is sort of red where it's really flat and white where it's really steep. And you can sort of see that we get our brightest colors along the top, along the sides of that crater. So it's going back to the original image. So all around the circle is where our highest values are, and then out in the plains it drops down. And it even picks up this sort of smaller secondary crater and a few secondary craters in a few locations. And it took a little bit of work, but it again came out looking kind of interesting, I think. And it's an interesting application of not plotting the geodata directly, but constructing something to go into that. So this one is also sort of interesting, and there's a certain amount of debugging of functions to make sure we got it as accurate as possible. And so this is looking at the magnetic field for the Earth using geomagnetic field data. And so we're looking at probably a pretty uniform grid over the Earth of sampling the magnetic field, and then we plot the streamlines, and you sort of see where things go from the south magnetic pole to the north magnetic pole, and we're going to sort of zoom in very closely, well, not too closely, but we're going to zoom in on the North Pole. And there are actually sort of three poles that are of interest. So the first is the North Pole. So that is, pick your longitude, 90 degrees. Latitude, that's this green dot directly in the center. And if you look, the streamlines aren't actually going to the North Pole. They're going to some other location. And what they actually converge to is called the dip pole. And the dip pole, if I remember correctly, is where the field is perpendicular to the surface of the Earth. And so that's where the everything is coming in. And in the end, we had to improve the resolution on geomagnetic model data a bit, and it stressed the GeoStream plot quite a bit. Sort of making sure that we're behaving correctly around this essentially singular point. Especially this this North Pole of at 90 degrees latitude is an interesting data point to sort of work around and deal with. And so that was a lot of fun and a lot of discussion about what things mean and what they, how they're represented and whatnot. And then this one is sort of interesting because it's, I mean, to some extent, it's just a stream plot of wind data, and we've looked at that before. But what makes it interesting is that this is using an interrupted projection, the orange peel good Homolocene projection. And so this is mainly here as an example for people who might want to sort of see how this sort of thing can be done in general. And the way that this is done is that in an ideal world, we would say, genome projection goes to orange peel or something, and this would just work. But what actually happens is we have this is stitched together from a bunch of individual maps. And so we have different projections and different parameters for the projections. It's all the same projection, just different parameters of where it's centered and whatnot, and how much of it we're showing, to sort of construct this this map as a whole. And I'm going to copy the parameters. We'll see if it actually copied. Right. So there's 8 components to this map. And you can sort of pick out where some of them might be. So there's, I think, a division along here. But so each of these parameters is feeding into this good Homolocene projection based on where it's centered and where the grid coordinate system is centered and whatnot. And then once we had that, then it was relatively easy to construct the stream plots and show them back together. The interesting thing is that you couldn't use show of the geographics because it would sort of undo the work, because it would say, oh, you're asking me to combine a bunch of maps with different projections, so the first thing I've got to do is convert them all to the same projection, which defeats the purpose. And so we had to do it a little bit lower level of converting the maps to sort of normal graphics and then combining them and setting the plot range to show everything. But it was an interesting application. And then the final example we're going to look at is using some data we found on where wind farms are located in the US. And so each of these dots represents a wind farm. Each wind farm has some number of turbines in it. And so you get a lot, around the Midwest, and some on the coast, and some in the Northeast, and surprisingly few in the South east part of the U.S. And so we're going to create a smooth histogram of the wind farm locations. We're going to restrict it to the contiguous U.S. And we sort of see that it peaks in Iowa and perhaps southwest Minnesota and whatnot. And that's sort of interesting, where the wind farms are the most dense. We're in Illinois, and there are certainly wind farms in the area, not in Champaign-Urbana exactly, but go 50 miles from here in multiple directions, and there are multiple wind farms. And so I thought it would be interesting to look at the wind data as well. And so I arbitrarily picked, January 1st, I'm going to get the wind data at a single point in time, and plot the vector field. And conveniently, the strongest vector is right here in Iowa, where our densest collection of wind farms is. We can overlay the vector field on the GeoSmooth histogram, and there's very good matchup of sort of where the strongest vectors are from Texas up to Iowa, Minnesota, Nebraska, and then across the upper part of the U.S. to the northeast. Not much wind that day in the southeast part of the U.S. where we don't have any wind farms. And so my conclusion based on a single, data point is that the people who are deciding where to put the wind farms in the U.S. know what they're talking about. They know what they're doing. It would potentially be interesting to create, perhaps a vector field or a separate plot of what the aggregated over time strength of the wind is, not just on January 1st. But even at looking just a single day, it matched up way better than I would have expected, than I could have expected in terms of where the wind is strong and where the wind farms are. So that was very satisfying. And so now I'm going to go ahead and look at the questions, the chat a little bit. And I'm going to start at the beginning and then work my way forward. And let's see. Right, so the ever common request for improved GeoTIFF support and importing to Geographics, which I know is on the list, and I don't think it's coming for 12.1, but it's certainly something we're aware of and are thinking of. Let's see. It'd be nice if dynamic geographics worked even more in the cloud, which, the unspoken part of that question is that dynamic geographics works in the cloud front end now. And so you can use dynamic geographics there. There are still things that aren't supported in the cloud version of dynamic geographics that are supported in desktop. And in particular, some of the styling and it doesn't support all of the primitives that desktop does. In particular, things involving inset or textures or whatever on polygons are going to be a bit more work to get working with the library, the JavaScript library that we're using in cloud. And okay, so Carl is saying that he uses geostyling of Geo Image a lot. I'd be curious if you can send in and to support with a note to pass it on to me. What sorts of things you're doing with geostyling Geo Image, just out of curiosity. And let's see. Okay, so GeoSmooth histogram is, as mentioned by Carl in chat, it supports weighted data. Weighted data. I know 12 had a few bugs with geosmooth histogram and weighted data and geohistogram and weighted data that I believe should all be fixed in the next version. But in general, there's weighted data is not a bad way of representing data in geo. The main downside is that I don't think you can have a so say a multi-geo position or an entity class as the first argument of the of the weighted data. And so you sort of have to list everything out explicitly. But it's not a bad container for that, and we try to support it as much as we can. Let's see. So stuff bleeding over into the ocean, we talked about multiple times with region function. We really like that solution of saying, here's the entity, or possibly here's a polygon, and computing with that automatically. And so there's a question about whether we can project the geo elements onto the map. And so for Geo Bubble Chart, the answer is not really. So there are things that you can do building up geographics by hand that would allow you to map, say, the flag of the flag of each country to the polygon of each country. And I'm sure there are examples of that in the documentation, and we'll see if I can find one quickly. So I'm going to start by looking at geostyling. Since that's the sort of directive that would allow you to map an image onto a map. So this is the Geo Image that Carl was mentioning that he uses a lot, and so this, as I said, allows you to map, in this case, the flag onto the polygon for the U.S. Image is going to be similar. The difference is whether the image gets distorted according to the map projection. And so you could build up a map of the world where every country was its flag, manually by using geostyling and polygon, and a bunch of these, one of these per country. But it doesn't really make sense for Geo Bubble Chart, because the bubbles for Geo Bubble Chart, in order for them to meaningfully convey their information about size, need to not be distorted. And so you really don't want those to distort more than they do in order to convey size in a meaningful way. And so I think that's the answer to that question. And I'll wait a moment to see if we have any other questions. But thank you, everybody, for taking about an hour out of your day to join me as we look at some of the geo things, some of the geo visualization functionality we've added recently. As I was saying, it's sort of a continual process of improving and extending the geographic data and visualization and core functionality. I know that I've learned a lot over the past few years about geography and cartography that I had no knowledge of prior to that. It's a really fascinating area. And with regard to Geographics 3D, it comes up now and then. Well, I'm sure we'll get to it eventually. With what priority or timescale, I'm not prepared to say right now. But it's an interesting question, and it may end up being, a separate set of globe-related functions or something rather than 3D, because there's the question of, so say GeoPlot 3D, is that a globe or is that more of a Cartesian, closer to list plot 3D sort of thing, where you aren't really taking the curvature of the Earth into effect as well. And both cases are useful. So it's just a matter of how you tackle it and how you package it and parameterize it, and how you work with it in general. But again, thank you everybody, and we'll stop here and enjoy the rest of your day.